We're now going to look at directed networks. Now, a directed network is also known as a digraph. It's a network with arrows on each of the edges to indicate a direction. So you can see we have a direct network here showing the results of a competition between A, B, C and D. So these might be teams that are playing off against each other. So the arrow was always going to point to the losing team. So you can think of A defeating B here because A is firing an arrow at B. So that's a good way of thinking of it as defeating B. And likewise you can see that A also defeats C. Okay, and the other thing to notice here that all of the arrows are heading towards B. B is not defeating anyone, so B does not win anything. And likewise C is defeating D down here, and it's also defeating B if we loop around here. However, C is beaten by A. Okay, so we can see here that A beats C. Now we can show this information in what's called an adjacency matrix or a connectivity matrix. Now, unlike when we were dealing with the topic of matrices and we were looking at transition matrices, we had the word from at the top and to at the side. Well, it's the other way around here. So we have from the side here and with the word to at the top. So we can see that from this matrix we've got a series of zeros and ones inside. Now those ones, or those elements which are ones, represent the edges in our network because it shows there's a connection. For example, from A to B there is a connection, whether you go from A to B or whether you go from B back to A. So each of these number ones represents a single connection between the nodes or vertices in our network. You'll also notice that there's a direction implied by this. For example, from D we can reach towards A and towards B. So from D, we go back up here, we can reach towards A, so the arrow heads towards A, and we can also reach towards B. And because each of these numbers represents an edge, we can total those elements up, and that will give us the total number of edges. Now you may wish to pause at any time because you, in your notes, you don't have, for example, this matrix or connectivity matrix here. So you might like to pause and try to draw this yourself and then come back and check it. Okay, so if you've done that, you'll notice that A reaches out towards B and it also reaches towards D. So over here I've got a connection from A reaching to B and also reaching to D, and I've filled the other ones with zeros. Likewise, if we look at B, B is reaching towards C, and that's the only one it reaches towards. So over here B reaches across to C, so I put a 1 there, and there are zeros in the rest of that row. Likewise, we can fill out the rest of these. So C reaches to D, but is beaten by B. D defeats B, it's beaten by A, C and E. Let's just look at why that one makes sense. D defeats B, so here we go. D reaches out to and defeats B, but it's beaten by A, C and E. So if we look at over here, it's beaten by A, C and E. You can see over here D, if D is reached to, it's beaten by A, C and E. So you've got to get used to this 2. These are the ones that have been reached to, and along this column all of the letters that head towards that are the ones that are beating it. So again we've got A, got C heading to D, and we've got E heading to D. We'll now look at the concept of reachability. Now, if one point in a network is said to be reachable from another point in a directed graph, this is true if a path exists between the 2 points. Now, if you examine the diagram that we have here, over here, if I can just get my thing to work. Sorry about that. So one point is reachable from another if you can get to it. So if you have a look over here, you can see that B is reachable from A. So we're looking at things from B's point of view. So B is reachable from A, and for example C, you can see, is reachable from A as well. A can reach towards it. C is also reachable from D. Now, if a node or vertex is reachable from another point in a single step like that, we can construct a reachability matrix using one-step paths, and we'll call that R1. Okay, it's not R to the power of 1, although interestingly we'll see that that does actually turn out to be the case later. But we'll call it R1 for the moment, and we're going to construct, as I said, a reachability matrix for each of these. So we're going to do an R1, we're also going to do an R2 and an R3. And an R2 means how many ways can you reach a particular vertex in 2 steps. An R3, how many ways can you reach it in 3 steps. So let's start with the R1 reachability matrix. Right, so if we have a look over here, we'll notice that remember, we've got from on the side and to on the top. So we're going to reach towards A, B, C and D from A. So from A, we can see from the matrix that we can reach towards B. So B is reachable from A, and also C must be reachable from A. Let's check the diagram. Is B reachable from A? Yes, it is. And is C reachable from A? Yes, it is. A can reach out towards C. Now you might like to think of it as a bowman on the side who is reaching towards, with his arrow, firing arrows from each of these vertices. So for example, if he's firing an arrow from B, he's able to reach C. If he's firing an arrow from D, he's able to reach A, and he's also able to reach C. And these reachabilities are one-step reachabilities. He's able to reach them from D, he's able to reach A in 1 step, and he's able to reach C in 1 step. Now for the 2-step reachabilities, you'll notice that there are a lot of zeros in here, not as many ways we can reach in 2 steps. Now if we look at one of them, up here, we can see that if we were situated at A, we're able to reach C in 2 steps, and there is one way of doing that. So this means we are reaching from A to C, and there is one 2-step reachability. There is one 2-step reachability. So if we're at C, we can reach C from A in 2 steps. Now how does that happen? Well, here's A. A reaches towards C in 1 step to here via B, and then that's the 2nd step to C. Now there isn't any other ways that we can get from A to C in 2 steps like that. We can see we can get from A to C in 1 step this way, and we can't get to C in this way because the arrow is pointing the wrong way. Now the other 2-step reachability we see here is that B can be reached from D. So D reaches out towards B, and it can get to B as a two-step reachability, and there's one way of doing it. That's why there's a 1 in here. So let's look at that one. D reaches out to B, so B is reached from D in 2 steps. We go up here. Can B be reached from D in 2 steps? Yes, it can. Okay, from D, we go across here via A, and we are able to reach B in 2 steps. So just again, D is the one firing arrows, and it can get to B, fire an arrow at B, so B is the one that's being reached in 2 steps. And there's one way to do that. Okay, so it's starting to get a little bit more complicated, because we're now going to look at an R3 matrix, which shows the number of ways we can reach from one vertex to another, but in 3 steps. So I might just get you to have a look at the graph and try and picture the graph as we look at the 3-step reachability. Now you'll notice there's only one element in here other than a 0, and that's over here. So that means C is the one being reached. The arrow is being fired by D. So that means C is reachable from D in 3 steps, and there's one way to do it. That's why there's a number 1 here. So C is reachable from D in 3 steps. Let's see if that's true. There's C, there's D. Can we reach to C in 3 steps? 1, 2, 3. And that's the only way to get from D to C in 3 steps. And so we've got a 1 in our matrix down here. If there was more than one way, we'd list the number of ways here. So we've mainly seen 1s as the elements, 1s or 0s, but you can have other numbers. Okay, so what we now do with our R1, R2 and R3s is we can literally add those matrices together to get what's called a total reachability. Now you'll always be, if you're ever asked to find a total reachability matrix, it'll say using R1 and R2, or R1, R2 and R3, it'll tell you which ones you need to add together. So alright, so if we just add the corresponding elements up in the way that we've added matrices before, we'll notice that, for example, in this position here, we've got a 1 there, and we've got a 1 there, and we've got a 0 here, so those elements add up to give us a 2. Alright, so we add the corresponding elements to find the total reachabilities. And because reachabilities is based on columns, we're going to add the numbers in the columns. So we can see that A has a total reachability of 1 if we add up all the elements in that column. So down here, we'll fill that in. A has a reachability of 1. B has a reachability of 1. Here's another one. So that's a reachability of 2. Okay, sorry about that page change. I must have pressed the wrong button for a second. Okay, in any case, that was the same as what I said before. So B has a reachability of 2. We can see that C is the most reachable. It has a reachability of 2, 3, another 3 is 6, so its total reachability is 6. Now notice that down here we've got that D has a total reachability of 0, so that means D can't be reached either in 1, 2 or 3 steps from any of the other vertices. And if you go back to that diagram up here, you can see that there are no incoming arrows towards D, so nobody can reach it, and there's whether it's 1, 2 or 3 steps. Looking at our next example, let's see which vertex cannot be reached from B. You can see there the answer is G cannot be reached from B. Let's see why that's the case. If we try to get to G from B, we notice that we can travel along B, can travel this way to C, this way to D, this way to A. Can't get to G here because the arrow is going back the wrong way. Is there a way to get to G this way? Let's follow this path. We can see again we're blocked because the arrow only allows flow in the direction from G to F. So we can't get to G from B. Now what I'd like you to do is try to construct these 1- and 2-step reachability matrices, and you can check back and see if you've got the answers correct. Okay, let's look at a situation now where you've been given the adjacency matrix or the connectivity matrix for a network with 4 vertices. Now straight away we can see that if we are at A, firing arrows, we can reach B and C. From B we can only reach C. From C we can reach A, and we can reach to D. And from D we can reach B and we can reach C. Now the idea is, can you draw a diagram to show that? So what's the best way to do that? Well, you can see the diagram's been done here, but let's say I hadn't already done it. What I would do is I would start by just marking in 4 vertices, because I need 4 vertices, A, B, C and D. And you just spread them out perhaps into a square. And now we're going to start over here at A, and we're going to reach towards B, so we'll need a connection from A towards B, and I'll put in the arrow. We can also reach from A towards C in a single step, so we can reach across here and put in an arrow, and now we'll systematically work through the rest of the vertices. So from B we can only reach towards C. From C we can reach towards A. And we can also reach towards D. And from D we can reach to B. Doesn't matter if they cross. And from D we can also reach to C. And that way we've produced that diagram. Now just examine this 2-step reachability matrix based on the diagram and see if it makes sense. We can see that, for example, we can reach from A towards C in 2 steps, and this one tells us there's one way to do that, to reach from A to C in 2 steps. So up here, if I reach from A to C in 2 steps, here is a 2-step path that does it, and it looks like that's the only 2-step path. So that's why I've got a 1 there. Whoops.